Hello class, welcome to the next lecture on signals and systems. In this lecture we will be continuing with our basic operation on signals, and this time we will be dealing with the operation on the independent variable. Okay, not variables, just independent variable. Right. So let's jump in right away. The first one is time scaling. Okay. Time scaling is, let me write it down, y of t is equal to x of at. Okay, x of at. So what is happening is basically we are picking up, suppose we have a signal like this, let this be x of t, and to construct y of t from this, what we are doing is we are not taking signals from all t within, suppose a to b, but we are taking specific values and combining them together, right? Something like this maybe, or sometimes maybe something like this. So what is happening is, let me just right, we have the original signal x of t. Suppose let x of let y of 1 will be x of a, y of 1.1 will be x of a into 1.1, right? So we are mapping every value here from minus infinity to infinity, right? We are mapping every value of time from minus infinity to infinity for y of t. We are mapping from x of t. It can be zero value or a non-zero value depending on at which all points of time x of t has a value, right? So basically we are taking something and putting it here. So the thing is that because this is a continuous signal, no matter how tiny an increment is there, instead of 1.1 it can be 1.01 or 1.0001, right? So since this is a continuous signal, basically you can, for any interval, whether suppose if this is from 1 to 2, right, or it is from 1 to 1.5, or it is from 1 to 1.1, or 1 to 1.0001, the thing is you can find infinite samples within this. So we are not losing much. We are basically, what we are doing is, depending on the value of a, we are either stretching this signal or we are compressing this signal. That is what is time scaling does. That is, we are taking samples from certain values depending on the value of a, right, and we are mapping it into another signal. So depending on the value of a, it is either compressing this particular signal or it is stretching out this particular signal. So let me just redraw this, right, and we will take a signal that we are familiar with. Okay, let's take a triangle 0, 1, 2. Let this be 1, x of t. Okay, suppose I want to find y of t is equal to x of 2t. Okay, so what will y of 0 be? It will be x of 0, this one. Okay, what will y of 1 be? Y of 1 will be x of 2 into 1, which is x of 2. That is again 0, 0, 1, again 0. what will x of y of 0.5 be? So we have taken y of 0, y of 1. Now let's take y of 0.5. It will be 2 into 0.5, that will be x of 1, this value. Right. Similarly, what will x of y of 0.25 be? It will be, what will it be? It will be x of 0.5, which is whatever value is coming here. Similarly, like this. So basically, right, what we have done here, we have compressed, and the value, amplitude value doesn't change at all, right? That is the overall value. What we have done is we have compressed this signal, this particular signal that we have, which was stretched out from 0 to 2 to 0 to 1. We have compressed it. Now let's take the same signal, right, 0 to 2, 1, 2, and let's now write y of t is equal to x of t by 2, that is 1.5 t. Okay, again similarly y of 0 is 0 only. What is y of 1? It is x of t by 2, x of 1 by 2, that is what is coming here. So let's 0, 1, 2, it is this one, right, this value. What is x of 0.5? It is, sorry, y of 0.5 is x of 0.5 by 2, that is x of 2.5. What is x of y of 2? It is x of 1. So what is coming here? What is x of y of 3? Y of 3 is x of 1.5, whatever is coming here, and this will be x of y of 4 will be x of 2. So I think you get an idea right here, that is we are stretching it out. Let me rewrite this at x of 0.5 t. So from this I think you can get an idea that if a is less than 1, 0 less than a less than 1, what is happening? We are expanding, or we are stretching out the signal. If 1 or let's say a greater than 1, what are we doing? We are compressing the signal, right? So you may think like here actually the signal is there from only 0 to 2, right, the original signal, but we are getting signal from 0 to 4. Where are these extra samples coming from, right, or extra points coming from? That was what I was saying initially. Since it is a continuous signal, for any interval of time you can get infinite number of values, samples, right? That is how you are able to expand this, right? And if you are able to maintain that continuous signal as a continuous signal, you can do any of this. But in real life it is not possible. You will have some loss of data once you compress, because in real life you cannot store infinite number of values, right? Anyway it will be limited. So once you have a certain size, suppose 0 to 2, if you want to stretch it over 0 to 4, you will have to make up some data, or you may lose some data. Anyway, theoretically this is possible for continuous time signal. So now what happens for discrete time signals? It will be y of n is equal to x of kn, right? And and similarly here also, here it is not compression or expansion. Let's see a question, right? A simple example. Suppose we have our sample signal like this. Okay, so I'm marking my 0 here. 1 2 3 goes on, -1 -2 -3 goes on like this, -4, etc. So let this be y of n. So sorry, x of n. So what will y of n is equal to x of 2 and b? X of 2 and b, what will it be? It will be what? X, y of 0 will be x of 0 itself. So let this be 1 and 0.5, right? What is x of, sorry, y of 1b 0? What is y of 1 is x of 2, which is again 1. What is y of 3? It is x of 6, which is again 1. Similarly for the minus side also, right? -2, -4, only particular samples will be taken. So actually here we are losing some data here. Ultimately, if you are having a finite sequence, and you can consider this as compression, but the thing is that in discrete domain you are having some data loss for k is greater than 1, right? For k is greater than 1, you are having some data loss. Then what about the case for 0 less than k less than 1? Is there a data loss? There won't be, because see, whatever value, time values 1 2 3 -1, whatever it will be, it can be made as some value of k into some value of suppose 2, the value 2 or 1. If k is equal to 0.5, y of 2 will be having x of 1, right? Or if it is 1/3, then y of 3 will be having x of 1. The only thing is that there will be some extra zeros in between, like suppose right, suppose k x of y is y of n is equal to x of 0.5 n itself. Then what is x of y of 1? Y of 1 is equal to x of 0.5, right? That is not existing here. That is a non-existent value in the signal. So what happens? A 0 will come there. So basically that here, that also you can say like, okay, it is being stretched out. If you are taking a finite sequence, you can say it is being stretched out. Only thing is that some extra zeros will be there. Extra zeros will be present in between every sample. But for k is greater than 1, definitely there will be some data loss, because all of these samples may not be accommodated in the new signal, right? Even for the continuous case, if you are taking a closer look into it, some of these data will be lost, but since it is a continuous signal, that loss won't be very significant, okay? Because we are having infinite samples or point values in this gap itself, even though we are losing something, it won't be much of a problem. But for discrete values, it is a real issue, right? And whichever real life problem we are solving, it will be coming into this domain, discrete domain, because if you want to store any value digitally, first you have to convert it into a discrete value, right? And you will be storing finite number of samples, and from that, if you are trying to compress, you will be losing data. That is why, for example, if you have some movie or image or video or even songs or whatever, if you are compressing that to reduce the size of the file, the quality will be reduced. You are actually losing data, right? This is the same thing, same process is happening here. So the next thing is called as reflection. Okay, so y of t is equal to x of minus t, and y of n is equal to x of minus n. What is happening? Reflection, the name itself it gives a hint. Suppose this is our 0, 1 and minus 3. Let this be 1. This is our x of t. So our x of minus t will be 0, minus 1, 3, 1. We are just flipping. The signal along the x-axis, sorry, y-axis, right? Or that is, we are flipping the signal from the time origin, right? Simple operation, flipping. That is called as reflection. It is like taking a mirror reflection of the signal and taking the y-axis as the mirror. Now, what is the significance of the y-axis? Y-axis means t is equal to 0. T equal to 0. That is the significance of the y-axis. Next one is time shifting. Time shifting, let me write y of t is equal to x of t minus ta, or t0, t minus t0, and y of n is equal to x of n minus m. Okay, so in the name itself you are understanding that we are shifting the signal in time. So let me just write it there. T0 and m is positive, implies the signal is shifted to right side. That is, the signal is delayed. T0 and m is negative, signal is shifted to left, signal is advanced, right, shifted left. This also we'll see with an example here. Okay, suppose we have the signal 0, minus 1 by 2, 1 by 2 and 1. Let this be x of t, right? So what is x of t minus 2? What is x of t minus 2? That means just let's do it the actual way. So t of x of, let this be y of t. So what is y of 0? Y of 0 is x of 0 minus minus 2, that is 0, right? What is y of 1? That is x of 1 minus 2, that is minus 1, again 0. What is x of y of 1.5? That is 1.5 minus 2, that is minus 0.5. So we have a 1 here, right? We have a 1 here. What is x of y of 2? Y of 2 is 2 minus 2, which is x of 0, which is 1. Right? We have a 2. We have a 1.5. And what is y of 2.5? That is x of 2.5 minus 2, which is x of 0.5, which is also again a 1, right? and from this, okay, you know, obviously from here it is 0, and let's confirm what is x of y of 3. Y of 3 is x of 3 minus 1, which is x of 1, which is 0, right? So this is right. So if you see, this is 2.5. You can see nothing else is happening. The only thing is that each and every point of this particular signal is being shifted to the right by this much value. Okay, what would happen if this was x plus 2, sorry, t plus 2? What would have happened? It would have shifted leftwards, right? It would have been minus 1.5, minus 2, minus 2.5 with this value as 1. It would have been shifted left by 2 units or each point. That is why this 2 is t0. That is what is being mentioned here. That is, if this shift is positive, right? And remember, when you are saying t0 is positive, we are considering x of t minus t0, right? Right, we are considering t minus t0. That is ultimately what should be happening. It should be x of t minus something, right? If it is x of t minus something, it means the signal is shifted to right. And if it is, I am saying it is delayed because originally it should have started from minus 1 by 2, but now it is only starting from 1.5. That is right, it is starting at a later point. Similarly, if t0 is negative, that means it will be x of t minus some negative, that is ultimately t plus something should come. Then it is being shifted to the left. I am saying the signal is advanced because it is starting early. It should have started at minus 1 by 2. Now it is starting at minus 2.5. The same concept is therefore the same concept is therefore our discrete signals also. Suppose we have our signal like, right, let's call this, okay, 0, 1, 2, minus 1, minus 2. If this is x of n, then x of n plus 2 will be, what will x of n plus 2 will be? It will be x of n plus 2 will be what? 0, 1, 2, 3, 4. Each and sorry, n minus 2, n minus 2. Each and every point will be, sample will be shifted to the right by 2 values. So x of minus 2 becomes x of 0. Similarly, minus 1 becomes 1, like that. Same concept is applying here. Okay. The one thing you have to notice, now that we have seen shifting and scaling, right? Sometimes you will have to, not sometimes, most of the times you will have to use this together, right? So that is, you have seen y of t is equal to x of at, and y of t is equal to x of t minus t0. So now what if we have something like y of t is equal to x of at minus b? That is, you have to scale and you have to shift. Okay, if such a question comes, don't worry, in the next lecture we will discuss problems so that you have a hold of this. I'm just giving you the direction steps here so that when the question comes, you won't be blindsided. Okay, if this happens, step 1, shift. Okay, this is the same for discrete also. Y of n, follow the same thing for discrete also. A of n minus m. Shift implies v of t is equal to x of t minus b. Then scale. Okay, that is y of t is equal to v of at is equal to y of at minus b, right? Because this at is applying, we are only applying it to t here, right? T of b. You can do it the other way also. You can scale first and shift later, but the first thing is that it will be difficult. You may not be able to use that technique always for discrete signals, because if you are scaling first and shifting left the second, what happens is that you may have a shift of 2/3 or 1/2 or something. You may have some fractional shifts, so that you won't be able to implement in a discrete signal. For discrete signal you should have integer shift, so that is why it is always advisable to shift first. So this is a method you can follow for both continuous time and discrete time. So I strongly suggest you shift to this routine, this regimen. Okay, and scaling you apply later, whether it is a reflection or a simple scaling, because reflection also you can consider it as a scaling for our purpose, because it will multiplication by -1, right? So that is the operations on signals of for the independent variable, time scaling, reflection and time shifting. So in the next lecture we will look at some problems regarding these questions, shifting and scaling, things like that, and after that we will move on to elementary signals, and from there we will start considering systems. Okay, thank you.